gives me a nice introduction to the next topic, because here the data was collected at different times and also in different locations, and we had to account for this. But there's different ways to account for this, and this can also be done by linear mixed models, or sometimes mixed effects models make much more sense than what we did here by just including them as factorial predictors. So we are talking about random grouping factors, and then kind of what we might already know, intercepts, random intercepts and slopes. And finally, we will also use continuous correlation structures. So here, the assumptions for a linear model. Yesterday, we have seen what we can do if the third, the fourth, and the fifth, the third or the fourth are not met with your model in a generalized linear modeling framework. Now we are looking what can we do if the first one is not met. So if all these observations are not independent observations, but if they are maybe collected at different locations, and yeah, so maybe this data set comes from 4 locations, so your data is grouped. So if your observations have been sampled in some kind of groups, and this means there is a categorical predictor with m levels, for instance here 3 levels, and each of these contains multiple observations, then these observations in this level here are not independent, right? So they might be influenced by some collective property of this location. So there might be structural or kind of unobserved conditions in these groups, but we still want to make inference on the whole population. So what can we do here? Yeah, first some classical examples how your data can be structured in such a way that I would say, okay, you have to account for this maybe in a mixed effects or random effects model. First, yeah, your data is collected at multiple locations, and each locations might have like different environmental conditions. So you should account for this. All the data has been collected at in different years. Yeah. Same argument in each year, the whatever conditions are different, and you want to account for this. Or your data is a collection from different researchers. Every individual might have collected the data a bit differently. Then the next one, this is kind of, I would say, important, especially in more, for instance, in medical research, in clinical trials, where often you have multiple measurements for the same test object. So you should account for this because, yeah, these observations per individual are not independent, and otherwise you would have this classical pseudo replication. Yeah, all kinds of other structuring variables in your experiment, units, or interestingly here, yeah, sometimes even species can be considered as such a grouping variable if you want to make predictions or model something on a higher level, for instance, on the family level, but the actual data is collected from different species. There's many ways to describe this. In the literature, you find all of them. I guess there's even other descriptions I don't know, or I haven't included here. Almost all of them, I would say, are synonymous. So for me, mixed effect model or mixed model, hierarchical model, multi-level model, partial pooling model, they're all kind of the same. The only one that sticks out here is the last one here. That's a random intercepts model. It's only different in a way that it kind of specifies something. So all the other models are a very general term about, yeah, how to include grouping variables. Only the last one here tells me, oh, I want to include them in a very specific way. I want to do only random intercepts. But all the other ones here are, at least from my perspective, totally the same. So let's talk about what is a random effect. And we will use an example here. I have this from the Carey book about Bayesian statistics. So we have some observation for some snake species. We measured their weight of 200 individuals. However, these data are collected from different sites across France. So 9 in total. And we just want to measure the mean body weight, the mean individual weight. So very simple question, and also potentially very simple model. So what is the correct statistical model here for estimating species mean weight? So just fitting only an intercept for all of these 200 data points without correcting for site, just fitting intercept isn't correct, because we have this first assumption of linear models. This is not met because these observations are not independent. They come from grouped data. Okay. You say, okay, well, why not just include this variable? So we are fitting weight depending on site. But what would this produce? Which kind of output would this generate? So this basically fits an individual mean for each site. So we would get nice predictions for kind of the site-specific mean weights, also their credible intervals, all good, but we do not get an estimate per se for the total mean weight, and also no confidence intervals for this. So we want to include this in a statistically more correct way. We start with looking at this first model here. And I call this complete pooling, because I pool all the data and I ignore the fact that they come from different sites. So let's look at the mathematical description of the model. Each data point is fitted with a joint intercept or joint mean A, plus some error term epsilon here. We have 200 data points. We assume that all the residuals come from a joint normal distribution, and I can specify a prior for the intercept here. I can also specify a prior here for the sigma, but that's not important right now. Right, so here we have the first line is deterministic part of the model, or rather just y equal to a is the deterministic part of the model. Then this epsilon here is the stochastic part with a normal residual distribution. And then we have the prior. So we're ignoring the predictor site. We pool all the information across all the levels of site and fit a joint intercept. And we get a value because it is informed by 200 data points. This value comes with very small uncertainty. Right? The more data points we have, the more certain we are about all the data's mean. So just pooling all this information here will result in very small credible intervals, so high certainty about this value. However, we are overconfident here because this data is not independent. So this is the other model, and I call this no pooling model. Here we include site as a predictor. And I do not pool any information across sites, right? So if we look at the mathematical description, we see that basically each site gets its own mean. And each data point is modeled as the intercept of this data point's site, plus some error term, and the rest of the model is identical. But now I not only have one intercept, I'm fitting 9 intercepts, one for each side. So each of these intercepts can be given a prior. Here they are all the same. However, they don't have to be the same. I can also say, okay, each side, whatever, maybe I have information there, I want to have a different prior. But that's actually also not that important. The important is just I specify a prior with some values I have. So these intercepts are basically independent, right? So they're all given their own intercept. And here you see the credible intervals here are a bit larger, because now this site level mean is not informed by 200 data points, but maybe just by 20 data points. So here the credible intervals are a bit larger, so there's higher uncertainty about the site-specific means, because per site we just have maybe 20 data points and not 200. Okay, now we are doing a trick, and this is all you need to know about, or how to understand what a random effect actually is in the Bayesian framework. Therefore, I like it so much. So we just replace the prior here, which has some fixed numbers. We replace this by these numbers by some parameters themselves. So here a site is the same. We just replace the prior for each A by, for instance, normal distribution. I mean, it's commonly done with a normal distribution. So all the intercepts, so the site-specific means, they have a joint mean and a joint standard deviation. And this is from for each level. So here from 1 to 9. So we have 2 additional parameters. We can assign both of them priors, but these are now 3 parameters of the model itself. So they are estimated in the model footing process, in the MCMC, or also maximum likelihood, if you want to write this down as a maximum likelihood problem. So the only thing we did is replace the kind of fixed prior distributions with something where the kind of parameters of this prior distribution are the site-specific, are parameters which are also estimated. We sometimes call them hyperparameters. And these 2 parameters have a meaning. Here we have mu A, right? So this is the overall, so the mean of all the site level means. This is an own parameter. And this is the kind of overall estimated body size here. And so they all have their site-specific intercepts, but we also get an overall intercept here, and sigma determines how much these site level intercepts vary. And in classical LME4 notation, or also in brms, we can code this as 1. So this is just this overall intercept plus site-specific deviation of the intercepts. We can write this model a bit differently. I mean, the model is the same, we just reparameterize it. So instead of having here priors on these actual intercepts, or here having the intercepts here, we replace this by the overall intercept plus the site level standard, plus the site level discrepancy or deviation from this. And then now the site level deviation here is kind of this random term, and we assume that it comes from a normal distribution, but now centered around 0. So if you replace AJ by the overall mean plus the site level deviation, you will arrive at this model. And these effects now, so these are the difference between the overall mean and the site level mean. These are the parameters here, these random effects now. So it's the same model, just the rearrangement of the coefficients. And here these deviations are kind of, the random deviations from the overall mean. We call this partial pooling because we are not fitting all of the sites separately, meaning we are not having this no pooling model, but we are also not pooling them completely. We are not ignoring the site, but we are allowing the site level deviation from the overall mean. So we are partially pooling information here across sites. So let's compare all of these three approaches. Here, first one, the no pooling. I just fit an intercept. Sorry, the complete pooling. The blue one is the no pooling. I just use, I'm estimating independent site level means, and then this compromise between the two of them. This is this partial pooling or random effects model. So first of all, let's look at the overall intercept here. Well, the red one, we've already seen it. Here we were overly confident about the uncertainty of this one, because we thought, it's informed by 200 data points, independent data points, but this is actually not true. So this is informed by 9 sites and by 9 site level intercepts. So here the uncertainty is much higher. And actually, this is the mathematically correct uncertainty. So the red one is overly confident, but the purple one here, the random effects model, describes the actual correct uncertainty of this overall. Okay, and then if you go on site level, there is no site level prediction for the red model, or I mean it's the same as this overall, right? So there's no difference between sites. So we are just comparing the no pooling model now, and they are pretty close. However, if you look closely, for instance, here in the 7th site, we can see it quite nicely. So the 7th site is has a lower mean than all of the other sites, but we can see the purple one is a bit closer to the overall mean, and this also happens for all the other ones. So the in all the sites, the purple one, so the partial pooling model, here the site level prediction is drawn a bit to the overall mean because all of the levels inform each other. Right, so the blue one has the whole freedom of like having independent mean, so it can like fit the data here independently, whereas for the purple one, we have this kind of compromise between independent model fit and also drawn a bit towards the overall mean. And sometimes we call this shrinkage of parameters. So if we look at this on the random effect level, so on the kind of deviation from the overall mean, if we look at the model again, so either the side effects come from a normal distribution with this joint mean, or if we look at the deviations here, then this deviation comes from a joint normal distribution with a 0 mean. Standard deviation here is the same. Okay, we assume they are normally distributed. However, we could in a Bayesian framework also use a different distribution, but normal distribution here is the classical choice. So these are the nine dots here on this x-axis. These are the site level deviation from the overall mean for each site, and they kind of gather around 0, but there is some standard deviation involved. So this part of the likelihood would be increased if the model would choose that these random effects are very, very small, right? So if the random effects are very small, the standard deviation becomes lower and the mean is the same. And then the likelihood function here would increase, because if we kind of shrink it or if we make it more narrow, it has to be larger values, because the area here under this is always 1 because it's a probability distribution. So from this perspective of the model, these random effects would want to be as small as possible, right? To increase this part of the likelihood. It's this part of the likelihood here. However, if all of these side level means would kind of tend to the overall mean, then they wouldn't fit the data as well, right? So these random effects here will be some compromise between fitting the data as well as possible. This is done with this blue model here. But it also wants to have these random effects as small as possible. So it's kind of a compromise between kind of having small random effects. This would be good for this part of the likelihood, but also compromise with a good model fit. So fitting, or the model kind of wants to draw them apart from each other in such a way that they fit the data the best. So a random effects model is always this compromise between the random effects being close to each other, but also fitting the data as good as possible. So it's always this, this kind of compromise between the two of them. There is always a trade-off. So these random effects, or the standard deviation of the random effects, and also the residuals of the model, they kind of partition the variance in 2 different levels or 2 different hierarchies. Right? And this is also why we call it a hierarchical model. So the overall variance of the data can be separated between the among level variance and the within level variance. So here we have this on the side level, this among side level variance. So this is how much does the mean, or how much of the predictions, the side level predictions, differ from the overall mean. And here we have this sigma A, that's the parameter that estimates this side level difference. But in each side, we also have the data points. They have a deviation from the side level mean, and this is the residual variance here. So it's on observational level. Yeah, and here the total variance is kind of split up into this among and this within variance. They both act on different kind of hierarchical levels. And both of these sigmas here are parameters which are estimated. Right? If you wouldn't have this as a random intercept, but just fitting the side level mean, then you wouldn't have an estimator here for the sigma A, because it wouldn't be part of the model. All of the A's would fit independently to the data. If you fit this model in BRMS, the output is quite similar to what you might know from LME4. You get all of this information in different lines. So first on the side level, here you do not get the actual side level means. You just get information how much do these vary. So here the variation of side level means is around 11. Then the regression coefficient here, this is the actual overall mean. So the mean weight is around 149. And here further distributional parameter, this is just the residual standard deviation, what we already know from all of the other linear models. The only trick we did here is replacing the prior with additional parameters which we are estimating in the model. And this is kind of the basis of all the kind of hierarchical modeling. And at least for me, I only kind of truly understand what a mixed effect model is once I started doing this in the Bayesian framework. Okay, so we continue. We can have also mixed effects models that usually denote models where we have not only random effects, but also other effects as well. So here in these models, I mean, the termination is not always so clear. So the effect we were actually interested in was the overall mean mass of a snake individual. And here in this case, this was the fixed effect. So the overall mean, and we can see this in this notation here, we are fitting the overall intercept. So this is the only fixed effect here, opposed to the random effect, which here is this side level deviation. So here this would be the, this random deviation from the overall intercept. So sometimes we would also call this deviation or the random intercept. Yeah, so these side level intercepts, these are the random intercepts. And side itself is the random grouping factor. We can include other predictors, and then we can decide how we want to include them. For instance, let's have the same data set. But we also measured length now, right? Sure, I mean, especially for a snake, it's pretty evident that the mass depends on the length. But we would be interested in mass differences while accounting for length. So this would be other differences in mass which are not depending on length, right? So we're including length as an additional predictor to maybe account for or to maybe measure all the other differences here, which are not included just in length. Okay, well, yeah, should we just include length here and not using side? No, we shouldn't do this because, again, we know that all of these individuals are not independent. On the other hand, we could just fit a classical ANCOVA type of model, so continuous predictor in interaction with a categorical predictor. But also this wouldn't be the statistically correct model because we do not get an overall slope, right? So we are interested maybe also in the overall slope here and not just in the site-specific regressions. So we will go through the same steps again. First, how much of the information we are pooling across sites. So the first one is, okay, we are ignoring the site predictor, meaning we have just a linear regression here. So this first half here is my deterministic part of the model with intercept and slope. We have a classical residual standard deviation, and we have priors for the from the model parameters. So we just fit one slope and one intercept, and this is classical linear regression, or we would also call it complete pooling in this framework. However, we would be kind of overly confident about the actual strength of this intercept because we would wrongly assume that they all come from, so that all of these observations are independent. Second model, this would be a classical ANCOVA analysis. We just include the categorical predictor site also as a fixed effect. So in a classical framework, here both, if I include this as an interaction, we get a site-specific intercept and a site-specific slope, but they are independent of each other. Again, we have priors. They are the same for all sites, but you could also choose different ones that do not have to be the same across sites. However, they are true priors, right? So we don't have a parameter here. We have to specify these priors. So basically, we are fitting a regression for each site separately, which is fine. I mean, this model is not incorrect. However, we will not get an estimate for the overall intercept and the overall slope. right? So we are basically just fitting them separately. 9 different regression models here, all put together in one model. But we can do the trick again. For instance, if we do the trick again for the prior for the intercept. Here we replace the intercept prior by some 3 model parameters. So the joint, intercept, and the standard deviation. So these intercepts here will not be independent anymore. They come from a joint normal distribution, and their parameters are estimated during model fitting. The slope here is the same. We have the slope here is the same for all of these regression lines. And yeah, we would write this in this way. Here, length, this is a fixed effect. There's no kind of random or hierarchical structure involved here. However, we have the sites or the intercepts per site are allowed to vary in this random effects framework. And we would say, okay, this is a random intercepts model to emphasize that we only allow the intercepts to vary, but not the effects here. So not the slopes for the variable length. Yeah, you can again write this in this slightly different form by just reparametrizing. Now we have the random effects. They are the deviations from this overall intercepts, and we can write this here that these deviations come again from a normal distribution. It's the same normal distribution just, but now with a mean 0. And we can yeah, write this like this. It's the same model. Yeah, so this basically gives me these site level regression lines. The slope is the same, but the intercepts are allowed to vary in this, not completely independently, but in this random effects framework. So yeah, you can look at the overall regression here, which uses the mean intercept and the slope, and this is called the marginal prediction, because we are marginalizing out the predictor site, right? So we could also say we're averaging over the predictor site, and then we get this regression line here, which involves a bit more uncertainty than the model where we do not include site at all. And so here we have a bit more uncertainty because we kind of correctly included that these data points are not all independent. And yeah, this is called marginal prediction. But if you here plot these on site level, right? So including the random effect, this is called a conditional prediction. So conditional on site. And I think you can imagine where this is going. Yeah, again, here a picture of, yeah, these are parallel. They are allowed to vary in the intercepts in this random effects fashion. But now we can do the same for the intercept, for the slope as well, right? So instead of having the slope being 1 for all of the sites, or being kind of an independent slope for each site, we write this in this way. So also the slopes now come from a normal distribution where their joint mean and their joint standard deviations are model parameters and are estimated in the MCMC in the model fitting process. And now this mean of the intercepts and this mean of the slopes, this gives me here this regression lines for the marginal prediction, right? So marginaling or averaging over sites. And you see that the uncertainty increased a bit more even. Yeah, we get a predictor for the overall intercept, or for the mean intercept, and for the overall slope, the mean slope here, while still correcting for the discrepancy between sites. And if you look at the yeah, you can again write this in this other way, where you have like the overall mean intercept and its deviations plus the overall slope and its deviations. The model is still the same. You could also look at the conditional predictions now. So you see that the slopes are allowed to vary as well. And this is called a conditional prediction. So conditional on the site level here. There's just one, yeah, they are varying. There's just one technical detail. I mean, it's not so important. If you fit the model in BRMS, it is not fitted in this way. So the deviations for the intercept and also the deviation for the slope, they are not independent. So they do not come from two independent normal distributions, but they are estimated or are assumed to come from a multivariate of a two-dimensional multivariate normal distribution where intercept and slope have some correlation. The correlation is estimated also in the model here. Right, so they are not assumed to be independent. They are assumed to, I mean, if the intercept, or sorry, if the slope goes up, then usually the intercept goes down. So there might be some negative correlation here. And this is estimated as well. So let's compare these models again. Here, we would ignore the predictor site. We would be overly confident about the about the confidence intervals of the slope and also of the standard of the intercept. But if we include it in this way, the uncertainty of the mean slope and the mean intercept is quantified correctly. If we compare this against the no pooling model, right? So this is this ANCOVA type of analysis, just lengths in interaction with site. Basically, they're getting all their individual intercepts. So they are basically independent from each other. Intercepts and slopes. And it's conceptually the same as doing 9 separate regression analyses. Here you can't see it in these pictures because the differences are very minor. But here also the intercepts, not only the intercepts, but also the slopes are drawn towards this overall joint intercept. And again, we sometimes call this shrinkage, the shrinkage of parameters towards their joint mean. Again, here, the difference here is quite minor. We can't, at least I can't spot the difference by eye. However, if there's some differences in sites, for instance, an unbalanced design, so this is the same analysis, but here in the 9th site, we only have 3 observations. All the other ones, they are fine, right? So they have about 20 data points. You can fit a regression there, no problem. But here for this 9th site, the regression is really bad. Even with priors here, I'm not even certain if there is a positive relationship of mass and length, right? So it could also, from the model here, it's very uncertain. It could predict, or in the range of credible predictions, there's even a negative relationship between a mass and length. So very little about this mass-length relationship here for this level, if we fit it in this ANCOVA type way. However, if we apply this random effects framework here, random slopes and intercept, this regression line here is informed by all the other ones as well, because we know this site level slope and site level intercept, they come from a distribution which is connected to the other intercepts and slopes. So it is informed by the other ones as well. And here we get a decent prediction line, even in the presence of just 3 data points. So we are actually borrowing strength from other levels. And this is why, that's another case why these mixed effects models are often used to make better predictions on the site levels here. So far, I only talked about continuous predictors. I mean, the grouping factor in here, so the site itself was always a factorial predictor, right? So we have 9 different sites. Site is a categorical predictor, but the additional predictor here, length, this was a continuous variable. But you could have random intercepts or random effects model also if you have a categorical predictor, and this is displayed in this this figure which I used from Harrison et al. That's also a nice overview review paper on random effects models. So here there's a continuous predictor. Here this is only random intercepts. So the intercepts here are allowed to vary randomly, whereas the slopes are identical. And random intercepts and slopes here means that the lines do not have to be parallel. And the same you can have if your treatment is a categorical. Here it just has 2 levels. It could also have like more levels. But then again, the effect from the one to the next level in this random intercept way, the effect here would be the same. So just random intercept, no random kind of slope or effect of the treatment. But here random intercept and slopes, or kind of also randomness for the effect of treatment, would mean that they don't have to be the same, because yeah, they're allowed to vary around this overall slope, which is displayed here in a dashed line. Yeah, the output here again is similar. So here we have also this predictor length. Again, the first block here are the multi-level parameters. Here we just get the standard deviation for the intercept, the slope, and also the correlations. Here the correlation is very low. But what we're usually interested in is this overall effect of length right here. So this would be the kind of fixed effect. This overall mu b, so this would be the fixed effect of length, which we are actually interested in. And finally down here, this is just the residual, which is the same as for all of our linear models, the standard deviation of the residuals here. Okay, so here site was just one grouping factor for which you accounted, but we also can have problems with a multiple grouping factor. And there's different levels or ways to combine them. So here, this is the same example, 9 different sites, but now we have an additional predictor, which is time. We here have 5 sampling campaigns. Again, I don't have like information about the time span, or I don't want to acknowledge like the time span or the temporal intervals. I just say, okay, that's at 5 different, whatever, 5 different dates, I went into the field and collected the data. So this can be fully crossed, right? So site and campaigns can be fully crossed, which means that each campaign visited all the sites, or it can also be partially crossed. Not all campaigns visited all sites, which means that, on the other hand, not all sites have been visited by all campaigns. We are still interested in the overall mean, the overall body size of snakes. And if we say, okay, site and campaign are kind of independent, we can just include them both as additive random effects. So we'll account for the individuals coming from different sites, but also having been observed in different campaigns. So you might know this notation here. You can just add one effect for site and also add one effect for campaign. And in the mathematical formula, you can do it the same. So here the individual data point is modeled as a joint mean plus a site level deviation plus a temporal or campaign level deviation. And each of them are now modeled in this random effects framework. So the site level deviation will have some standard deviation, and also the campaign level deviation will have some standard deviation. Both of them are free model parameters and are they can have priors, and they are estimated in the model fitting process automatically. If we look at the hierarchies, we can again imagine that this divides the total variance into among and within level variance. And so this is the overall mean. Then we have the site and campaign level. Here they are kind of both on the same level, right? So there's not site is more important as campaign or the other way around. It's just, yeah, you have some deviation per site and you also have some deviation per campaign, and they just add up. So you see this in this formula, it's mu A plus the site level deviation plus the campaign level variation. So both of them contribute to this site campaign level variation, both on the same level. They're just independent and add up. And then you have this observation level variation. Here, this is then each data point's classical deviation from the model prediction. So all the randomness in the data, which is not already explained by site and campaign. If you fit this model, again, the output here is very similar. Here you just get two different values for how much this site level here is the campaign is the first one, the campaign level deviations and also the site level deviations. And you can read the importance from the estimate here, right? So if there is a stronger deviation between sites, right, it's almost 10 times stronger than between campaigns, which kind of makes sense, right? So you don't expect like in different sampling campaigns to have the snakes to have strong difference in body size, whereas if you go to different locations, there might be strong differences due to environmental conditions. And yeah, for this model, at least this would be the one thing you are usually interested in, the overall effect or the overall intercept here. That's the only kind of fixed effect we're having in this model. And the uncertainty is correctly accounted for here. Then there is another way these random effects could be structured. So again, the same example, but now we use a different predictor. So 9 different sites, but they again are grouped in 3 different mountain regions. Right, so each site can only belong to one region. There's no overlapping regions here. And also at least one of the region must have 2 or more sites. Otherwise, site would be the same as region, so we couldn't distinguish them. So we have this hierarchy, right? Here, very, very classical different levels of spatial aggregation. So we can say there's a nesting of the factor site and the factor region. And we can account for this. Here, the first line, this would be how you would specify it. So you say region and then slash site. This means site is the lower hierarchy, region is the higher hierarchy. But this is nothing else than having a random deviation for region. Right, so this is the first level of the hierarchy. So from the overall mean, there is a region-specific deviation, and then additionally, there is a site-specific deviation from the region, which you could write here as if we had a predictor, which is the interaction between region and site, we can just write it like this. So here, first the region level deviation, and then plus the site level variation, which is nested in region. And otherwise, looks completely the same as the crossed before. You can, if you want to look at this again in this hierarchical framework. Yeah, here we have the overall mean. Then we have a site level, or no, a region level deviation, which is associated with its own sigma. And then here you have the site level deviation from the regional mean, which is associated again with a site level sigma. And finally, you have the observation level deviation from this prediction here. So you have split up the variation in different levels of hierarchy. And again, here the output looks the same as for the crossed, because you can write this nested as a crossed effect of region and the combination of region and site. So the output here is the same as with the crossed, just you have one standard deviation for the regional level and plus the standard deviation here of the site in region level. And again here for this level, we actually would be interested here in the intercept, so the overall mean and its associated uncertainty. So here for this for these different ways of having like this grouping factors nested or crossed, I just used a very simple just fitting the intercept, the overall mean, but you could also have models where you have more complex or more predictors here for which you want to estimate the effects while correcting for these grouping factors. Yeah, nested or crossed is often a question that appears when you want to know how to analyze your data. But yeah, it's actually not that different. I mean, if you have some structure where the one is kind of nested in the other, this is just a shorthand for writing this as crossed effects, where the first factor is the first factor and the second factor is kind of the combination of both of these factors or the interaction. If the second factor is already uniquely labeled, right? So for instance, if the 9 sites are called 1 to 9, then they are already uniquely labeled. But if you would have like in region 1, you have site 1, 2, 3. In region 2, you have also site 1, 2, 3. Then they are not uniquely labeled. Then you kind of have to kind of or it's automatically uniquely labeled for you by this interaction. Okay, I think we are done for having categorical predictors as random effects, right? Whenever you have some grouping of your data with some factorial predictor. However, this grouping can also be more flexible. You can also have continuous correlation structure, which I will just briefly go into. We are not using this here later on. I just want to briefly describe this because often you will have kind of spatial or temporal autocorrelated data where you have time or latitude, longitude actually as continuous predictors. So think of the same data set again, but instead of having like different sites, we now want to include the actual latitude and longitude and latitude here as a kind of grouping predictor. I mean, there are no actual groups, there's just a continuum in space. And how can we do this? There's several ways actually to do this, but you could also model this to this kind of hierarchy in this hierarchical framework. And here, this quote by Tobler, I think it's called the first law of biogeography. I think everything is related to everything else, but near things are more related to than distant things. And here you would use a spatial autocorrelation model. So think of here are your 9 different sites. They are arranged in longitude and latitude. And the closer the things are, the stronger is their correlation, right? So here, both of these sites, they will have their strong correlation because they're very close. These sites will have a very weak correlation because they are quite far. And the correlation itself can be modeled as a function of distance. So here we have two predictors, longitude and latitude, but differences between sites can be just modeled as distance. So the Euclidean distance, for instance, and the lower the distance, the higher the correlation. And if they are far apart, we do not assume that there's any correlation, so close to zero here. And we can model this. It's just one way of modeling it. By saying, okay, I want to fit my data, right? So all the 200 snake individuals, I want to fit their joint mean. And I can model this relationship here by putting it in the residuals. So I say the deviation from this joint mean here are not independent anymore, right? So this would be, if they would be independent, we could just do a regular linear regression. However, we say, okay, they are not independent. All these residuals are not from a normal distribution with a zero mean and a standard deviation, but all these n data points actually come from an n-dimensional multivariate normal distribution. So we have an n-dimensional vector of residuals. So here, two-dimensional, 200 residuals, and they are not independent, but they have pairwise correlations. And this is expressed here by this correlation matrix. So this is an n times n correlation matrix where kind of the pairwise correlations here, so these are the pairwise correlations, are modeled by, for instance, this correlation structure here. So we are modeling, we are putting this correlations between locations, we are putting this into the residual, right? So you're not estimating this as a kind of predictor here, we are just putting it, we're saying, okay, the residuals are not independent, but they have some correlation structure. And you can model it like this. So this is an exponential function decreasing with distance, and it has an additional parameter here, theta. This just determines how quick or how fast this correlation function here declines. This would correctly describe that the residuals here are not independent. Yeah, we have the parameter sigma. This is again the standard deviation. We have this additional parameter theta, which is how quickly the correlation drops with distance. So that's one model for spatial autocorrelation of residuals. You can define the same model for temporal autocorrelation by having like time as a continuous predictor. Works the same. The only difference is that you do not have like 2 dimensions here, but it's just 1 dimension of time. However, this specific way is not implemented in BRMS yet. You can model this yourself in Stan or Nimble. But so the problem here is this model usually is pretty slow. Because in the model fitting, in each step of the sampling, you have to calculate the inverse of an n times n matrix. And calculating the inverse of a matrix is the kind of most costly linear algebra operation out there. So this can be very slow, especially if you have like even a moderate amount of data points. So 200 data points, 300, 400 data points, you will already kind of feel the impact that the model fitting would be very slow. But there's alternatives. For instance, INLA is another program that does this very efficiently. Another quick solution is not to have this being estimated in the model fitting process. Right, so here, this is depending on some parameter theta, which is estimated as well. You can instead, in BRMS, hand over the correlation matrix by calculating it beforehand. Basically, just means you choose this theta yourself. There's some ways through variograms to get a good idea how this parameter, or what value this parameter should have. And then you have one correlation matrix, which is a constant, and then you can put it in BRMS, and then it works quite well. Statistically, this is not 100% perfect, because this parameter theta usually also has some uncertainty, and you should also estimate this during the model fitting process. But this is a fast and efficient solution. And there's other solutions in BRMS. Usually people, I think, go to generalized additive models for this correlation structure. So there's either having the fixed correlation model. The second one, you can use Gaussian processes or generalized additive models. And this basically means that you do not put this correlation in the residual, but you have this as a function here itself, which is which doesn't have that many degrees of freedom and is kind of more efficient to do. But usually also, I mean, GAMS, I would go for the MGCV package here because it's very, very efficient. It's not Bayesian, but yeah, we are getting into the realm where we kind of see the computational bottleneck sometimes of Bayesian statistics. However, this kind of general mathematical framework is very powerful. You can model spatiotemporal correlations, but also correlations along the phylogenetic tree. However, this innovation framework can get slow with a number of data points, and here INLA is really efficient. I've never used it or always wanted to check it out, but it's another Bayesian software which is specifically designed for this context. Okay, we have worked with grouping factors and also a brief overview on kind of not a grouping factor, but a grouping continuous variable. But for these classical grouping factors, these classical factorial predictors, there's often this kind of question, do I model something as a random or as a fixed effect? And classically, the interpretation was very strict and also very kind of simple, I would say, easy to remember. Well, if you're interested in the overall means, overall effects, but you must account for the non-dependence of the data, then you use this as a random effect. Right, so either just a random intercepts model, or if you have some other factor or other variable, also random intercepts or random intercepts and slopes. However, if you are actually interested in the differences between sites, then you wouldn't use a random effects model. You would just model a site as a classical variable. And then here you would have these ANOVA, ANCOVA with additive or ANCOVA with interaction type of models. Right, so when you are actually interested in some effect, you can model it as a fixed effect. If you just want to account for it, you model it as a random effect. However, especially in the Bayesian framework, this has been a bit relaxed. So you can also use random factor models for different purposes, for instance, to correct for unbalanced designs and get better estimates on site level. So what's Bayesian about it all? Most popular package, I would say, is LME4 to do this. It will use maximum likelihood to estimate these parameters. However, to my experience, not often, but sometimes it just don't converge. It just won't give you value. And here in these cases, I always kind of have the same advice. Maybe first try it in another package. For instance, GLMMTMB is also very good for this, or in BRMS. And in BRMS, I must say it works almost always quite well. You get a correct quantification of uncertainty on all levels. So LME4, I think in the current version, for some parts of the model just doesn't give you p-values in the first place, because they say, okay, this is an approximation, we are not very certain about it, so it doesn't provide p-values. However, in a Bayesian framework, you will always get estimates for uncertainty here. Sometimes there's some limitations in the frequentist framework. For instance, it will be hard to fit some model where your random grouping factor only has 2 levels. In a Bayesian framework, that is not a problem at all. You can easily fit models with just 2 levels of the random grouping factor. I would say the interpretation is, at least for me, more easy, understanding this in a Bayesian framework through the different levels of hierarchy. And additionally, I mean, classically, you say, okay, my random effects, my deviations, they are normally distributed. But if you model this yourself, for instance, in Stan, there is no limitation. You can also, model different distributions. For instance, if you assume that, all your effects are, maybe come from a log normal distribution or something like that. So to sum this up, in the linear modeling framework, Bayesian statistics does not free you from model assumptions. If your residuals are not independent, you must account for them additionally. If you don't do that, you will be overly confident, right? Or in the case of a frequentist analysis, you will kind of get small p-values. You're happy about it, but that's a false claim then. You are overly confident and you did not account for the structure in your data correctly. I mean, that's thinking hard about your data will reveal the random effect structure. That's often easier said than done, but the way of using crossed or nested random effects, this really should come right away from how your data is structured. In BRMS, writing formulas is just the same as LME4. This makes the transition very easily. And we didn't specify it here, but you can also use generalized linear models. In BRMS, you can even use nonlinear models while accounting for random grouping factors in this mixed or hierarchical way. And the cool thing is you can all of this, you can do all of this in just one package, which makes it easy to, compare models across different levels of hierarchy. Again, some literature. Here's a couple of papers which are interesting. So some introductory papers or tutorial papers among them for mixed effects modeling, and all of them are in the context of ecology. So I always made sure that these are ecology specific, ecology or biology, I must say, Okay. I'm continuing with the practical part. As always, please write your questions in the chat anytime. So what are we modeling here? What's the data? Okay, we have a data set from Wharton's ecology book. And we count invertebrate diversity, no, number of, so abundance of invertebrates from samples, from aquatic samples in different estuaries. But the interesting part is that each of the estuaries is either pristine or modified. Right, so an estuary can either be pristine or modified. And the question is there a difference in abundance between modified and pristine estuaries? And if you would just pool all these data into two groups, just modified and pristine, without accounting for the estuaries, you would kind of wrongly assume that all of these data points are independent. However, they are grouped by this grouping variable, so we want to account for this. Later on, I will use other variables as well. So here we will only use modified and pristine, but later on I will also use the variable temperature. And the models have some observations have NAs, but not in all the variables. So BRMS will exclude any row in the data frame which has an NA, no problem. But if you run different models with different kind of predictors or different combinations of predictors, then sometimes one data set will less data points than another one, because if you include a predictor which has an additional NA in a row which was okay before, then both of these kind of models would be with different data sets, right? Because they're maybe differing in just one line or something like that. And if you want to compare these models, you have to make sure beforehand that they are both run on the same complete data set. So here, I think the first model I'm running is just using the 3 variables, but the other one here introduces another additional NA. So now I will remove these from the model, also from the data set, also for the first data set, that in the end we can do model comparison. I want to fit a model where I have a different intercept for modified and pristine. So the model would be, I have a B, which is an intercept or joint mean for this differences in modified. So modified is either 1 or 0, or it's kind of modified or pristine. So we'll have 2 different joint intercepts here. Right? Modified is either 1 or 2. But I will account for this difference in estuaries. So this delta, so these random effects, random deviations, here has 7 levels, and these are the notations of these levels here down here. So actually there is some kind of nesting of like models in estuaries in this either modified or not. But we are not using this here because pristine or modified, this will be the fixed effect, right? So this is what we're interested in. And we are not particularly interested in the variation between estuaries. And therefore, we only have this grouping factor estuary here, which we use as a random effect. Yeah, so then the total number of species, again, classically normal distribution around the prediction and some sigma. But now we also have this hierarchical part. So the delta, these are the random effects, come from a normal distribution with 0 and the specific random effect standard deviation. Yeah, this is a kind of the whole mathematical description of the model, but we can just write it in just one line in BRMS, just as you would do in LME4. But let's have a look at the priors first. So this is the model we are fitting. We have a fixed effect from modified or pristine, a random intercept for estuary, And looking at the default priors will already reveal something about the structure, I guess. Where do I start? Okay, first line, okay, this means, is there a prior for all the effects? So class B means effects. No, there is nothing specified. Also, there's nothing specified for the specific coefficient predictor, modified or pristine. And for all the other stuff here, BRMS chooses default priors. So that's a prior for the overall intercept. And then sigma is the residual standard deviation, and SD here is the estuary random effect standard deviation. And BRMS takes care of that. So some default priors for all of this hierarchical model structures are already given. So we don't have to specify them unless we have a specific reason to. And classically, no priors given for the actual effect, so for the actual fixed effect we are modeling, so we can specify a prior there. And here I would specify a prior. So this is just the effect of modified versus pristine. So I assume, maybe there's some difference, but I don't know if it's positive or negative, and I associate this with a quite wide standard deviation. So this is actually a weakly informative prior. Okay. So we fit the model. We get a warning messages that, oh, here a couple of transitions ended with a divergence. Okay, what does this mean? This is a warning message you should take seriously. If it's just one or two, I wouldn't mind, but over 100, this is concerning. What does it mean? It means that at some point in the MCMC iterations, choosing a new sample, it didn't find a good proposal for a new sample. So it just continued sampling in another direction. That's not a problem if this happens once or twice or whatever. But if this happens 100 times, this means 100 of these samples are chosen in a weird way. So we definitely should take care of this. Okay, in the previous run, I don't know why, I just had 3 divergent iterations, but maybe I noted this down wrong. It's 136. We can specify that the MCMC samples more accurately. I just have to remember how this is done in BRMS. Control. And here one parameter is adapt delta. This just increases the accuracy. And I think I can specify it like this, adapt delta. So the default value is 0.8, and you can go up to 0.99999, whatever. It must be smaller than 1, I think. And the good way is to increase this to 0.9. Here we go, perfect. So whenever you have this divergent transitions, this means either you specified something wrong in your model, or just, that the posterior is maybe difficult to approximate, and this can easily happen in mixed effects models. But often this can be solved by using this different control parameter. This makes the sampling a bit slower, and it can be substantially slower if you have like a huge data set or a very complex model. But here this, was just a couple of seconds fitting in total, so this is fine. Okay, we look at the summary table and look at the R hat values to see, okay, they are fine. And here we have this separation in these different blocks of parameters. We don't get an actual display of the random effects, but we can extract them if we want to. we only get a display of the standard deviation of the intercept. So this is how much does the overall intercept vary between different estuaries after correcting for if it's modified or pristine. So how much does this deviate from the predicted intercept? Yeah, and here we see the intercept. So this is because it is a model with a categorical predictor. So the intercept is the mean prediction at modified. So for the red dots here, the mean is 37, something here, and the difference. So the pristine estuaries on average have like 9 individuals less, right? So there's higher abundance in the modified locations. Yeah, you should always look at these plots here, and especially in a random effects context, sometimes convergence is not guaranteed. So you should look if your chain run long enough and if they're mixed well. But here everything is fine. Okay, so as always, the summary table is not, well, in many cases, not fully describing all the model and not giving us all the information. Here we could, for instance, extract the fixed effects and the random effects. So the fixed effects, this should be just this fixed effects block here. This information was already contained in the summary table. However, the random effects, they were not fully displayed in the summary table. We only had their standard deviation. So with this command here, we can extract them. So here, this is the mean deviation per each level or per each location, also associated with the respective standard deviation. Okay, we haven't looked at, we haven't looked at convergence, but we haven't looked at how well the model fits the data. Again, we can use the conditional effects plot to do this. However, here we only get a display of the fixed effects part. Right, so this is the marginal effects plot. So it marginalizes or it averages over all the levels of the estuaries. So estuaries isn't even displayed here. We just have predictions. So the black ones and the observations, the other ones, the dots here for this fixed effect predictor. Okay, we can specify that we also want to make estimations on the random effects level. And therefore here we have to specify reformula equal null. So in general, that's a bit tricky, and it also took me a while to find out reformula equal null for all the involved function here always enforces using random effects. And if you say reformula equal NA, this kind of forces it to omit the random effects. Just one thing to keep in mind. So here this function automatically kind of uses the marginal. It does not include the random effects. So if we want to include it, we have to specify the reformula equals 0. So here we get predictions for each level of site or estuary. So this includes fixed and random effects. The interesting thing here now is, right, in each one, there's only data for either modified or pristine. However, the cool thing is now you could make predictions how this estuary or how this would change if you have like a pristine one and you would modify it in the same way the other ones were modified. right? So you get this predictions here already. Yeah, and also for all the other functions, you can either make predictions on the only fixed effects level, so marginalized or summarized over all the random effects, or to actually include the random effects, for instance, by specifying this. So the fitted will just give you, the fitted will always give you, including the random effects, but you can also specify to not include the random effects by specifying this here accordingly. And the same for instance, the R2 values. So I don't know which this one is. Let's check. Yeah, the base R2 will automatically give you the conditional one, so including the random effects. And yeah, specifying this here will actually give you the same. You can also specify to exclude the random effects. So just this would be the marginal R2, and it's always lower than the conditional R2 because it just includes the fixed effects and not the random effects as well. The same for the posterior predictive checks. Here they are done with the random effects, but you can also specify to only make predictions with the fixed effects. So, and since we are still in this nice linear mixed effects modeling framework, the performance package works quite well here. So we can use the check model function to check all the other linear modeling assumptions here. For instance, if the variance here increases or not, or if the residuals are normal, which isn't super great here, but I think it's also not completely off. There's one additional plot which can be helpful, and this is checking the quality of the random effects, or not the quality, but if they are normally distributed. And so you have 1, 2, 3, 4, 5, 6. Here you have 6 estuaries, so you will have 6 random effects, and they should be normally distributed. And here this checks the quantiles against the normal distribution. So classical QQ plot, also for the random effects only. Okay, so after we also checked the model performance, if it fits the data well, and so on, we can go back to the original hypothesis. And this was an hypothesis here on the fixed effect only. Right, so we put everything in the fixed effects, what we actually want to test here in this case. And this was, is there a difference between abundance, invertebrate abundance, between modified and pristine? And we can here see this in this one parameter. Let me check the summary table again. So here in this special case, we have the answer, or we can also see it in the summary table. So is there a difference between modified and pristine? This is the difference and the associated credible intervals. This actually covers 0, so I'm not 100% sure that there actually is an effect here. So we can look at the hypothesis function, and here we get a posterior probability of 95% that there is a difference. One more model. We talked about that there is a temperature effect maybe as well. So we want to include this to see, okay, well, is there a difference between modified and pristine when we also account for the effect of temperature? So here, again, this is the fixed effect we are actually interested in. We account for the level of temperature, and also we account for the differences between estuaries. So all this other variation which might be estuary specific, but is not explained by temperature alone. Otherwise, the model is actually the same. Also, the prior specifications are the same, right? So here you have all these mixed effect stuff. There are default priors by brms, and we specify a prior for the effect of temperature. Here, temperature is a continuous predictor, and we scale it. And also this difference between modified and pristine. Again, here are some divergent transitions. Again, I mean, with 5, I mean, this 5 is, I would say, still okay. So 5 divergent transitions of 4,000. I wouldn't kind of bother too much about this, but we could also specify to run this with a larger adapt delta. To get rid of these divergent transitions. Okay, and if we increase the accuracy here, we got rid of all of these divergent transitions. So we are still interested here in the difference between modified and pristine. And here in this case, by including temperature, the difference is a bit smaller. So let's first look at some model predictions. Right, so if we do not specify anything, these will just be predictions for the fixed effect part. So averaging over all these different deviations of estuary. And since this is temperature and modified pristine, temperature is a continuous predictor. So these will be 2 regression lines. And yeah, there's some uncertainty involved. And here in this case, we averaged out these different intercepts of estuary, but here we modeled these different intercepts of modified versus pristine. Again, you can enforce to also include the random effects in this conditional effects plots by enforcing this with reformula equal null. And then you get the predictions here for each estuary. Again, the difference here is the same for all of them. However, each of them has like a different overall intercept. Okay, yeah, so we included temperature. First, we could make model comparison between both of these models to see if temperature actually has an effect. And here in this case, the temperature effect is really small. So you can decide to include it or not. Going back to our original question, is there a difference between modified and pristine even after accounting for temperature? Also here, I think in this model, there's quite some support for this hypothesis. Yeah, if there's a difference in species or abundance here for these 2 types of treatment. Okay, so I think this is it for today. There is again an exercise, and there's a new data set which comes with an additional predictor, which is inner or outer zone. So this means, so previously we had multiple observations per estuary. And now we have an additional predictor to specify if the sample came from the inner or from the outer zone of the estuary. And also this can be accounted for. Here in this case, you can include this as another predictor in the model to see if the temperature effect, if the difference here between modified and pristine still holds, even when you include temperature. Right, so before in the model we fitted, now we have seen, okay, even accounting for temperature, we still found a difference here between modified and pristine, and you can go through the same steps in the exercise with this new data set, which is very similar, but includes this additional predictor of the outer and inner zone in each estuary.